step 3. All right, so step 3, don't be thinking about this anymore. That's closed. We are now thinking about from G3, so glyceraldehyde 3-phosphate. And I'll just put gly down there. And cetoheptulose, 7-phosphate, okay? And in step 3, we have transaldolase. So you can think Weird Al. Aldolase. You can also think...
Oh, did you want to start recording again?
I did.
Yeah, okay.
Good catch, though. All right, so transaldolase. Okay, transaldolase moves 3 carbons. We're in step 3. That's really nice. So we can math. So G3P becomes something with 6, which is fructose 6-phosphate. All right. And fructose 6-phosphate should be a really friendly looking molecule because we've seen it in glycolysis like 40 times while we were trying to memorize it. So fireworks around fructose 6-phosphate, it goes to glycolysis. It just goes off to glycolysis and is acted on, makes ATP, same thing we've seen it do before. Okay? Cetoheptulose 7-phosphate becomes erythrose. Don't judge my spelling. Rose 4-phosphate. All right, so we see 3 carbons coming off of the cetoheptulose and being added to the glyceraldehyde 3-phosphate. 3 plus 3 is 6. Fructose 6-phosphate goes and is made into ATP. Cetoheptulose 7-phosphate is the one that gave away those 3 carbons, so it's going to lose 3, and it goes down to erythrose 4-phosphate. Make sense?
Mm-hmm.
Okay. And now we see trans-ketolase again. Okay, and it's ketolase, all right? 2 carbons. So, now erythrose is going to be acted on. Fructose 6-phosphate is gone. It's left. It is no longer here. So, we are going to pull... All right, I told you not to look at this. I lied. All right. There. We're pulling a xylose 5-phosphate from earlier in the pathway in order to have the erythrose 4-phosphate exchange carbons with it. Okay? Trans-ketolase goes between erythrose and xylose. We've seen xylose before. It was earlier in the pathway. It's the same molecule. You'll notice that fructose has 6 carbons. Xylose has 5 carbons. I know in class some people were like, 10 carbons, I got that. Next step, 10 carbons, I got that. Last step, 9 carbons. Why? It was very traumatic. So the 10th carbon left with the fructose 6-phosphate, and we bring in a subpar xylose with only 5 carbons and a phosphate on the 5th carbon. That's what was going on. Okay? So xylose 5-phosphate is going to give 2 carbons to erythrose. Erythrose, I'm just going to put E4P. I am that person of lazy. All right. Erythrose 4-phosphate, then I'm going to erase that because it's changing into fructose 6-phosphate. This one, xylose loses 2 carbons, and so it becomes glyceraldehyde. That's a Y. 3-phosphate. Okay? And that's from xylose. So these 2 just exchanged carbons. And both of these are in glycolysis. Fireworks. And so that's where they go. They go back to glycolysis. They're digested or metabolized the same as any other glyceraldehyde 3-phosphate or fructose 6-phosphate, and they're made into energy. And that is the entire pentose phosphate pathway. What is the purpose of the pentose phosphate pathway? There are 2 things in this pathway. One is you make NADPH. Remember in step 1, you made 2 NADPHs. NADPH is kind of like a little activator dude. He goes around and turns things on. Something called glutathione is something that is turned on by NADPH, and that's glutathione gets rid of free radicals. That's pretty much what we're expected to know. Okay? The other thing that this pathway does, besides making NADPH, which can turn stuff on, and sometimes off as well, it just toggles stuff on and off. The other thing is it makes ribose. Ribose 5-phosphate, okay? So ribose 5-phosphate is used in DNA and RNA generation, and so whenever you're dividing the cell, you would want the ribose. If the ribose isn't used, then it will go through this pathway and be made into the glycolysis subunits. So that is the pentose phosphate pathway.